Okay, now that we've looked at a simple homework-like exercise to get a better understanding of what the direct stiffness method is and the matrices involved, how could we go about proving to ourselves the hand calculations that we did using SolidWorks Simulation? Well, it's actually quite simple. I started a new part, and for every node I'm just going to create a surface body, something like a plate or a plane, to help me in creating those nodes. And the size is arbitrary. I'll make them square plates. Again, the size is arbitrary, so let's just choose 6 inches. That looks fine. And we'll use surface bodies because they are the easiest to mesh for this type of problem. Our springs are going to be applied at the center, so let's start a new sketch and use split lines to create a vertex in the center of our plates. Okay, that's one plate. I need 3 more. And for that I will create a very simple piece of reference geometry just to give me a sense of direction. Now we can use a body pattern, a linear body pattern, with that little sketch stub. And every 12 inches we're going to copy our body, and we'll reverse that direction. Okay. So each of these surface bodies represents our nodes. Let's jump into SolidWorks Simulation and create our spring elements and solve for our displacements and forces, because that is what the direct stiffness method is. Just as the plate size doesn't matter, so doesn't the thickness, and for that matter, the material that we apply as well. Our global contact is bonded, but none of these bodies are touching, so it doesn't matter. Let's go ahead and create springs. Leveraging the vertices that I've created, it's very simple to attach those vertices and apply each of our spring stiffnesses. And we'll thumbtack that down so that we can easily and quickly grab the remaining nodes. And last but not least, the third one is also 10,000 newtons per meter. Okay. Our second node is where we're applying our load, and that's a normal load of 450 newtons. Total, not per face. Remember, we split the faces. And now we need to restrain the geometry at nodes 1, or the first plate, as you see here, and the last plate. And we're restraining these with translations and rotations because these are shell elements. But the middle 2 nodes, the second and third plate, also need to be restrained. We don't want them to wobble or flip. And I only want to restrain them enough so that there's relative motion in the negative z direction. So I'll choose a reference plane and choose 2 representative edges of each plate, requesting there to be no translations out of plane or no rotations out of plane. And that should be sufficient to restrain those 2 wobbly nodes. The choice of solver and the choice of mesher is inconsequential. So I'll just mesh it with the default elements, choose the default solver, and now we can go ahead and save our work. Okay. How do we know that what we've come up with from hand calculations are what we're coming up from the numerical calculations? Well, first thing we'll look at are displacements. And while our colors are helpful, we can get a little more granular. First of all, let's take a look at the displacement in just the z direction. And another tool that we could use would be to probe the vertices, or the nodes, where we've applied our spring elements. So let's choose the plate where we've applied a load. Here we see the value of negative 2.7 e to the minus 2 meters. Let's change our plot to reflect that in millimeters. So we have 27 millimeters in the negative z direction. At our third node, 18 millimeters. So that agrees with our nodal displacements from our hand calculations. In a similar vein, you could take a look at the reaction forces. The tool is very similar to probing. What we'll do is we'll turn on the resultant force vector, and for example on the very first plate, which is fixed, you can see an update in the force, 129 newtons, due to the spring element resisting the tugging of the 450 newtons. Choosing another node, about a 0 value. And so you can see it's very easy using SolidWorks Simulation to recreate the problem that we did in our homework exercise of understanding the direct stiffness approach. If you have any questions, please don't hesitate to call Graphic Systems. We'd love to hear from you. Thanks.